aspect of conceptual understanding of quantum mechanics, that is, what is the fundamental difference between the classical object and the quantum mechanical object. Once we understand this difference between the classical object and quantum object, then we will appreciate the motion and how the paths in the classical mechanics are completely determinate, while that in quantum mechanics, the path of a moving object are indeterminate. So after discussing this indeterminate quantum path, I will come to how the time development of a quantum mechanical object is described. Okay. Dynamics of the quantum mechanical object, and finally I will summarize. So, as I mentioned, the beginning of quantum mechanics is attributed to a statement given by Max Planck during a meeting of German Physical Society in the year 1900, that the radiation is absorbed and emitted in the form of discrete packet of energy instead of wave, in connection with explaining the observation of the black body radiation phenomena. So all of you are very well aware about this black body radiation phenomena. So instead of going into a very detail of this phenomena, I will put the problem like that, which is observable to everyone. Everyone must have noticed that. For instance, when we heat a piece of metal, then first it becomes red. If the temperature is further raised, it becomes yellow. If the temperature is further raised, then it becomes white. So this is basically the problem which is to be explained theoretically in the beginning of the 20th century. That graphically the problem can be shown as it is shown in this graph. If it shows the intensity spectrum of a metal piece which is heated at different temperature, then these kind of curves will be observed. So as the temperature is raised, you see, as the temperature is raised, the peak of the intensity curve is shifted toward the high frequency. Okay, in this diagram. Can you see this diagram? Frequency as well as the temperature raises, say from this observation, particularly while this intensity spectrum is like this. So what was the problem with classical physics? So for that purpose we see this. Classically, Rayleigh and Jean tried to explain this intensity spectrum, and they arrived at this formula that this energy density is given by this expression. All these are constant, 8 by kT equals nu square dt. That is, the energy density is proportional to nu square. Nu here is the frequency of radiation. So obviously, this graph between the energy density and the frequency will be a parabola, since this energy density is directly proportional to nu square. Just like y is proportional to x square in a parabola, so it is simply a parabola. So theoretically, the classical curve goes like a parabola, and at a higher frequency it tends to go to infinity. While the experimental observation, we notice that after an initial increase, there is a peak in the intensity spectrum, and then the further increase in frequency of the radiation leads to the decrease in the intensity spectrum, and finally at very high energy it becomes zero. So you see that classical theoretical results of the Rayleigh-Jean formula are drastically different from the observation. Even could not qualitatively produce the shape of this spectrum. So in order to explain that, or in order to avoid this so-called ultraviolet status 30, or in order to remove this discrepancy between the classical theoretical calculations and the experimental observation, Max Planck introduced the idea of the energy package, that is known as quantum of energy. And on the basis of that idea of energy package, Max Planck arrived at this formula for the energy density. You may see the difference between these two formulas, Rayleigh formula and Planck formula. In the Planck formula, there appears an extra factor H, what is now known as Planck constant. Okay. There is no such factor in the Rayleigh formula. Rayleigh formula basically is based on the law of equipartition of energy, which is not valid at the microscopic level. So a new constant is introduced, that is H, and proposed that the radiation of frequency nu possesses an energy which is proportional to its frequency. That is, the energy of a radiation of frequency nu is h. And on this basis, he arrived at this formula. And you can see very clearly from this formula, initially at very low energy. If we consider the very low energy region, then in the denominator, we see that when this exponent is expanded in terms of 1 plus this x plus x squared by 2 factorial and so on. So when nu is very small, then the term containing nu square nu cube can be neglected and only h nu term is there. Nu gets cancelled with this nu cube and it becomes nu square. That means this formula tends to be the same as the Rayleigh formula. So you can say the Rayleigh formula is basically a special case of this Planck formula in the low frequency limit. So you see that in the low frequency limit, both the classical result and quantum mechanical results are similar, okay, exactly same. But as the frequency increases, these two curves differ, and you see there is a qualitative agreement between the curves obtained by the Max Planck, by the Planck formula, and those curves. These are the experimentally observed. So you see the shape of this curve at a particular temperature. Initially it goes rise, there is a peak at some particular frequency, and then comes down. Similarly, here in the intensity spectrum calculated by using Planck formula, you see there is initial rise, a peak, and then decrease. So Max Planck was successful in explaining the black body radiation by proposing that the radiation is emitted and absorbed in terms of discrete packets of energy called quanta. But there was no physical justification for the existence of such quanta so far. The only thing about this formula is that it can successfully explain the observation regarding the black body radiation. The further confirmation of this idea of quantization was confirmed by Albert Einstein while explaining the important observation of the phenomena of photoelectric effect. You know the phenomena of photoelectric effect, a simple phenomena wherein light of suitable frequency is incident on the surface of certain material, then electrons are emitted from that material. This is the phenomena of photoelectric emission. And here this is the apparatus to study the photoelectric effect. So the two important observations of the photoelectric effects were, first thing, if we apply the retarded potential across the anode, retarded means negative potential to the anode, then experimentally it is found that at a particular negative potential, the current in the circuit will become zero. And if we increase the frequency of the incident radiation, then the potential at which the current reduces to zero, it becomes more negative. And if the frequency further increases, this potential becomes more negative. This potential at which the current in the circuit becomes zero is usually termed as the stopping potential. So one of the important observations one increase the intensity of the radiation by keeping the frequency same, but if the intensity of radiation is increased, then the stopping potential does not change. The stopping potential is independent of the intensity of the incident light. Now, what was the problem with classical physics in explaining these observations? The first thing is that when we increase the frequency of the incident light, classically the energy of the light must remain same, because classically we treat light as an electromagnetic radiation, and the energy of this radiation is proportional to its amplitude. Okay. In particularly, the energy contained in an electromagnetic wave or intensity of an electromagnetic wave is proportional to the square of the amplitude. So if we change only the frequency, keeping the amplitude the same, if we are keeping amplitude same, classically means we are keeping the energy same. If the energy of the radiation is same, then obviously the energy of electron emitted should be same. And if the energy of electron is same, then why the higher potential is required? The same potential may stop those electrons. So that means classical physics predicts that the stopping potential in the photoelectric effect experiment should be independent of frequency. But experimentally it is observed that the stopping potential increases with increasing frequency. So there was a clear contradiction between the classical prediction and the experimental observation. Secondly, classically, when we increase the intensity of a wave classically is simply the square of its amplitude. So if we want to increase the intensity, it means we want to increase the amplitude. And when we increase the amplitude, then we are increasing the energy. Okay. Because energy you see is given by the Poynting vector, that is E cross H. E is the electric field, H is the magnetic. So if we increase the intensity of either amplitude of either electric field or magnetic field, we are increasing the energy. And when the energy is increased, then obviously the electrons coming out from the surface must be more energetic. And in order to stop those electrons, higher potential is needed to stop those electrons. But experimentally it is found that the stopping potential is independent of intensity. So both of these results are quite contradictory as per the expectation of classical physics or the classical model of the light, that is electromagnetic wave. So in order to resolve this discrepancy, Einstein simply used the idea proposed by Max Planck, that is, the light is not a wave, it is in the form of discrete package of energy called quanta, or more precisely Einstein called these light particles as photons. And then he explained this these experimental observations through the simple equation that is nowadays known as Einstein's equation. Kinetic energy, here is the kinetic energy of the emitted electron. H nu is the energy of the incident photon or incident quantum. It is the same concept which is used by Max Planck. Okay. And phi is a work function. Work function means we know that electrons are bound in the material. So in order to take out the electron from the material, it is required to supply a minimum of energy which is equal to the binding energy of electron in that material, and that minimum energy is called the work. So it is quite simple as per law of conservation of energy. H nu is the energy of photon incident on the material. This H nu energy of the photon is used in two ways. In one way, first, some of the energy is consumed to make the electron unbound. That is to emit electron with just zero kinetic energy. So if the energy of photon is more than that, then the remaining part of energy will the kinetic energy of the emitted electron. Now let us see how this simple equation explain these observations. So, increasing frequency means increasing the energy of the photon. If the energy of the photon is increased, then obviously the electrons emitted will be of large kinetic energy. And to stop the electrons of large kinetic energy, a high voltage is required to be applied. That is, when we go from mu1 to mu2, that is mu2 is greater than mu1. So, high frequency photons are there with the frequency mu2, and high energetic photon emits the electron with more kinetic energy and hence more potential is required to stop. Similarly, if we go from mu2 to mu3, mu3 in turn is greater than mu2. So once again more potential is required. So it is as per the observations. Similarly, if we increase the intensity, keep the frequency same. If we keep the frequency same, then this absolute term in this equation remains same. The energy of the photon remains same. That is, the kinetic energy of the emitted electron does not change. So for the same electrons of same kinetic energy, same potential is required to stop. So this is how we explain the fact that the stopping potential is independent of the intensity of the electricity. So Einstein successfully applied the idea of Max Planck, that is the idea of this discrete packet of energy, in a very conspicuous way in this experiment, and he got the Nobel Prize for this simple equation. Then, in order to further confirm that the light behaves like a particle in the microscopic regime, Compton scattering experiment or Compton scattering phenomena further confirms that light is made up of particles. The Compton scattering effect is simply the scattering of high energy photon with a free electron. This process, obviously, free electron and high energy photon. The observation of this process of this scattering is this. Let us see X-ray photon. X-ray photon obviously are much more energetic than the visual light. So highly energetic X-ray photon incident on a carbon target and they get scattered. And the observation at different angle shows that at 0 degree angle we observe only one peak. That corresponds to the incident X-ray radiation, the incident radiation of this particular ray. If we change the angle from 0 to 45 degrees, then this single peak split into two, and this splitting becomes more and more pronounced as this angle is increased from 45 to 90, 90 to 135, and very clearly we see at an angle of 135 degrees, there are two peaks in this observation intensity space. The question is, how do we explain these two peaks at this angle? If we consider the classical picture of the X-ray, that is the electromagnetic wave, then what do we expect? We expect that X-ray radiation is absorbed by the atom of the target material, and then it is re-emitted in all the directions with equal probability and having with the same frequency as is the original frequency or wavelength light. That means we always expect only a single peak in the intensity spectrum, which corresponds to the frequency of the incident radiation. But experimental observation is that there are two peaks. So this second peak or the splitting of this intensity spectrum into two peaks would be explained by applying or by using the fact that the incident light is not a wave, it is a packet of energy that is called photon. And then the process of interaction between the free electron and the incident photon is considered as a particle-particle elastic scattering problem in classical physics. Okay, if we treat photon as a particle, electron as a particle, then by applying the simple classical physics or simply using the law of conservation of momentum and energy, Compton was able to arrive at a formula that the wavelength split will occur, and the split in wavelength is given by this expression h upon m naught c 1 minus tau c. Now, from this simple expression, one can explain these observations. That is, at 0 degree there is single peak. You see that when theta equal to 0 in this expression, then cos 0 is 1, 1 minus 1 is 0. That means delta lambda becomes 0, shifting wavelength 0. That is, the final wavelength is equal to initial wavelength. So, there is a single wavelength, so we have a single peak. Now, when the angle increases, let us say at theta equal to 90 degree. At theta equal to 90 degree, this cos pi by 2 will become 0, and the shift in wavelength is h upon m naught c. So, it means there is a shift in wavelength. And amount of shift is this h upon h. Means we will now have a wavelength whose final wavelength is slightly uh, more than the original wavelength. Now, one may here ask, okay, obviously there occurs elastic scattering and shift in wavelength is there. If there is shift in wavelength, why the original peak remains always there? This is very fundamental question which one may ask. Okay, due to this scattering, the shifting wavelength, no doubt, the wavelength will become shifted here, here, and more. But why always there is this original peak? This is because in the incident beam, a lot of photons interact with the electrons which are tightly bound with the atom of the target. In that case, the the photon which interact with the tightly bound electron of the atom, in that case, in this expression, this m naught, which is the mass of electron, is to be replaced by the mass of atom, because the electron is so tightly bound with the atom, then instead of considering the recoil of a single electron, the atom as a whole recoil. And when atom as a whole recoil, then this m naught is to be replaced by the mass of the atom. And if this mass is replaced by the mass of the atom, then this quantity delta lambda is negligibly small. It will become 0, because we know that the mass of atom, say in this case carbon atom, is thousands and thousands times larger than the mass of electron, because there is a nucleus contains protons and neutrons, and proton is roughly 2000 times heavier, neutron is also roughly 2000 times heavier, and there are 6 protons, 6 neutrons, so it is much heavier than the free electron, and hence this delta lambda becomes 0. So this peak, the original peak, that is the consequence of the interaction of photon with the tightly bound electron in the material, while the shifted peak is the consequence of interaction of the incident photon with the almost free electron, where a weakly bound electron is the atom. So this further confirms that the radiation is an incident photon. Okay. So you may interrupt me if there is some problem. If you find some difficulty at any time, you may stop me. Okay. I don't leave this spot.
Okay, sir.
Okay, thank you. Now, another problem in the beginning of 20th century was to understand the nature of matter. Okay, up to now, all these things, that is black body radiation, photoelectric effect, Compton effect, all these problems are related with the nature of the radiation. Okay, what is the exact nature of radiation? But parallelly, there was a quest to understand the nature of the matter also, how matter is at its microscopic level. So, atomic model was famous, and the most uh, successful model regarding the atom was proposed by Rutherford, that is popularly known as Rutherford atomic model, and obviously it is based on his experimental observation regarding the alpha scattering by the thin material foil. On the basis of the observation of the celebrated alpha scattering experiment, Rutherford proposed his model, that is the Rutherford atomic model, and according to this model, the atom consists of a heavy nucleus at its center and electrons revolve around this nucleus. But the problem with this model was that classical physics says that any accelerated charged particle always emits radiation. So the electron which is revolving around the nucleus is a charged particle in acceleration, because the curvilinear motion is always an accelerated motion. So the electron which is revolving around the electron is emitting energy continuously, and after emitting its energy it is coming closer and closer to the nucleus, and finally it must fall into the nucleus. That means the stability of atom could not be explained on the basis of the Rutherford atomic model. This problem was resolved by Niels Bohr by using once again the idea of quantization of energy. So up to now we have seen that Max Planck said that energy of radiation is quantized. Einstein used that idea to explain photoelectric effect. Compton used the same idea, that is the energy of radiation is quantized, to explain the Compton scattering effect. Niels Bohr extended this idea of quantization to the quantization of mechanical energy. Okay. He proposed that the energy of electrons around the nucleus is quantized. That is, the mechanical energy of electron is quantized. Already earlier we have seen that quantization of electromagnetic energy. Now that is extended to include the mechanical energy also. We propose that as soon as the electron orbits around the nucleus in a particular orbit, it moves in a particular orbit, it neither radiates nor emits. It can radiate only when it takes a jump from outer or higher energy orbit to lower energy orbit. And also it absorbs the radiation. By absorbing the radiation, it takes a jump from lower energy orbit to higher energy orbit. But the question was, there was no physical reason or no physical justification that why only specific orbits are around. Why not all the paths? Why not all the orbits? This question was answered or justified by Louis de Broglie by proposing that the electrons, while moving around the nucleus, behave like a matter wave. That is, electrons are no longer the particles, they behave like matter waves. Obviously, the electrons are to be associated with a wave, then there must be some wavelength associated with that wave, and the wavelength, by simply combining this Einstein energy equation, that is equal to mc square, and the definition of linear momentum, one can show that the wavelength associated with the electron is h by p, h by momentum. Okay. That clearly shows that larger the momentum is, shorter the wavelength, and shorter the smaller the momentum is, larger the wave. So Louis de Broglie proposed that electrons are actually not the particle following the classical trajectory. There are associated waves, electron waves, matter waves, and only those orbits are the stable orbits which accommodate a bigger number of waves. For instance, you see that one wave, two wave, three wave, four wave. So only those orbits which accommodate integer number of waves are the stable ones. Otherwise, if there is no integer wave means, if let us say three complete wave, fourth is half wave, then there will be a destructive interference between the different waves, and that orbit is no longer a stable orbit or valid orbit. So it was the justification given by Louis de Broglie for the existence of specific orbit in the Bohr atomic model. And this de Broglie idea of matter waves was confirmed experimentally by Davison-Zermer experiment. The person Davison-Zermer performed an experiment to confirm the fact that electrons are no longer particles, they are the waves. And the idea is simple. They studied the diffraction of electrons. The apparatus is this one. Here you see that there is an electron gun. This is an accelerating anode. Electrons are emitted from the electron gun and are incident on this nickel target. And from this nickel target, they get dissected and detected by the detectors. The simple process, if you compare this with the analogy of the diffraction by a diffraction grating, diffraction of light by a diffraction grating. So in the diffraction grating, there are various slits. So here various crystal planes, and the space between the two crystal planes acts as a slit. So it is a parallel slits, just like the same as the number of slits. So when the light incident on those slits, we observe a Fraunhofer diffraction factor. So here you see that if the intensity of the electrons detected at this detector is plotted as a function of this accelerating anode voltage, then the shape you see, the observed shape is like this, and this is the spectrum, which is nothing but the Fraunhofer diffraction spectrum. So the similarity between this observed spectrum and the Fraunhofer optical spectrum clearly indicates that the phenomena of diffraction has been occurring for the electrons in the lattice. And Bragg obtained the condition for the constructive interference, that is 2d sin theta equal to n lambda. Okay, d is the spacing between the lattice, theta is this angle of scattering, or you may say diffraction angle, and it is the order of diffraction. So you see there is a peak, then there are minima, maxima, and the order of maxima increases. The peak goes on decreasing, exactly the same shape or same curve which is obtained in case of the Fraunhofer diffraction, which your students perform in their BSc laboratory also. The diffraction grating experiment, and if you see the spectrum, they observe the same spectrum. So this analogy or this similarity between the observed electron diffraction spectrum and the optical diffraction spectrum clearly indicates that electrons are diffracted by the crystals. And the simple calculation, for instance, theoretically we know that the wavelength of the electron wave is given by h by mc, as proposed by de Broglie, lambda equal to h by p, h by mc. So we calculate from here the wavelength. H is the universal constant, that is 6.6 into 10 to the power minus 34. M is the mass of electron, is also a constant. V, the velocity of electron, it depends on the potential applied at this electron gun. So if in this experiment, Davison and Zermer applied a potential of 54 volt. So if we put here 54 volt, one H value of F, lambda comes out to be 1.67 x. This is the theoretical way. Experimentally, using this condition 2d sin theta equal to n lambda, it is found that there is a scattering peak at 50 degree. This is experimental observation. A peak at 50 degree. And if you put theta 50 degree relative spacing for this nickel target is this 2.15, then lambda comes out to be 1.65 angstrom. So you see the degree of matching, degree of agreement between theory and experiment. Theoretically, wavelength is 1.67 and experimentally it is 1.65. So only a difference of 0.02 angstrom, and at that time it is very good agreement. Okay. So this agreement between the observed wavelength and the calculated wavelength confirms the de Broglie hypothesis that the electrons are no longer the particles, they are in fact matter waves. Now, so electrons are waves. Now, if a wave is to be associated with a particle, then it is reasonable to expect that wave-like phenomena are localized in neighborhood of the particle. The question is, if we want to associate a wave with an electron, then it is quite intuitive that the wave-like phenomena should be in the neighborhood of the electron, where the electron is present. There is no fun of extending the wave from a point where electron is existing and taking it to up to infinity. So the wave-like phenomena are to be localized in the neighborhood of a particle, and it will therefore be necessary to deal with a wave packet, because we know that in a single wave, let us say we consider a sinusoidal wave. It will start from some point and it goes up to infinity, and you can see various crest, but if the electron is at some point in space, then there is no logic of extending the wave to infinity. So we have to construct a wave packet so that it is localized only in the neighborhood of the electron or any quantum particle. And a wave packet mathematically is constructed by forming a group of plane waves. If you superpose two plane waves, 3, 4, 5, up to say 1,000 and 10,000 waves, finally you will get a packet that will become a wave packet instead of the wave spreading up to infinity. And this wave packet description leads to uncertainty, which is naturally inherent in simultaneous measure of certain pairs of dynamical variables. So this wave packet description leads to uncertainty. And that is more precisely stated by Heisenberg in terms of the well-known uncertainty principle. For position and momentum, it states that delta x delta p greater than equal to h bar upon 2. Okay. Now, this is the basic principle, we may say, Heisenberg uncertainty principle, which actually decides whether the particle in consideration is to be treated classically or the particle in consideration to be treated quantum mechanically. There are just two possibilities. First one is that there are in nature particles of completely defined position and momentum. That means there are particles where the uncertainty position as well as the uncertainty momentum simultaneously, both these uncertainty are negligible. That's very good. Okay. We can apply classical physics without any hesitation. On the other hand, for the particles for which it is impossible to measure simultaneously position and momentum with a higher degree of accuracy than the uncertainty is allowed, then classical mechanics no longer works. One has to invoke the quantum mechanics. quantum mechanical particles. Then this uncertainty can be understood through this thought experiment. In order to uh, detect or in order to observe electron, one has to shine some light on the electron, okay, and then to detect using light motion. So minimum uncertainty position is given by wavelength of light. Okay, quite intuitive idea. Larger the wavelength, more will be the uncertainty position. Smaller the wavelength, smaller will be the uncertainty position. So uncertainty position is basically depends on the wavelength of the light incident of the electron to observe. So to determine the position accurately, it is required to use light with a short wavelength. As we have just seen, shorter the wavelength, smaller will be the uncertainty position and more accurately we can determine the position. But what happens when we use the light with a short wavelength? Then we know that according to the formula of Planck's law equal to h mu, shorter wavelength is large energy. So the light will be of large energy, and large energy light will give large energy to the electron, and so to determine the momentum accurately, electron must only be given a small heat. Energy to be imparted to the electron should be small. So it clearly shows that when we try to ascertain the position, we want to use the light of long wave, short wavelength. But when we use the light of short wavelength, it will give large momentum to the electron. So momentum becomes more uncertain. Okay, and vice versa. Okay, now we are in a position 2. So I think up to all the things were these were simply the background and already I think known concept to all of you. There was nothing new so far, just only to give a background idea. So up to now we have seen that there is a great confusion because classical physics says that light is an electromagnetic wave. Quantum mechanics says that light is a photon, that is a particle. Similarly, classical physics says electron is a particle, but quantum mechanics says that electron is a wave. So there is a great confusion. What is wave? What is particle? Whether electron is wave or a particle, whether light is wave or a particle. So instead of going into details whether electron is wave or particle or whether photon is wave or particle, it is now better to understand the basic difference between the classical object and the quantum object, so that we can say, instead of saying that electron, wave, particle, no need to say like that. Simply we will say electron is a quantum mechanical particle, photon is a quantum mechanical particle. But that we can say with certainty if we know what is difference between the classical object and the quantum. So, in classical physics, the concept of object is founded on the idea of an objective reality, namely that a material entity that has an intrinsic reality and its properties are inherent in the entity itself. That means the classical entity exists objectively and is a determinate one. So what does it mean? The objective existence. What is the meaning of the term objective existence and the determinate? The meaning is that whether we observe the object or we do not observe the object, in both the cases, the object exists exactly in the same state. That is the determinate state. Okay. So do you understand this term? The meaning of this? A classical object is an object which exists objectively, or in other words, that object is a classical object if its state of existence, its ontological existence is independent of whether it is being observed or not being observed. Okay, is this idea clear to you? Anyone, please?
Yes, yes, sir.
Okay. So in this diagram, as you see, a set of two apples. Basically, the set of two apples here represent a classical object. Okay, these two apples are classical objects. When this person is looking at the apple, they are in this state. But when this person is not looking at the apple, still they are in the same state. If you compare this set of two apples and this set of two apples, exactly they are same. There is no difference between these two set of apple and these two set of apple. Means whether one observes this object or one does not observe this object, the state of the object is same a determinate state. If the particle is such that its state of existence is independent of observation, then that is a classical particle. On the other hand, in quantum mechanics, the object has two forms of existence. When it is observed, it is definite and definite. When it is not observed, it is indeterminate and uncertain. And fundamental to the two forms of existence of a quantum entity is the act of observation or the process of measurement that connects the unobserved with the observed. Now you see here the clear difference. Classically, here you see in this diagram, a blurred sphere is shown, okay, where it is the most intense at its center, and as we go away from its center, it becomes less and less intense. So this is the quantum mechanical object when it is not observed. You see that when this person is not observing this object, this is in a uncertain and indeterminate state. So this basically diagram is showing an atom when it is not observed. Then this diagram schematically shows that the atom is everywhere within this darkened region. Okay. The atom is everywhere within this darkened region. But as soon as one observes this atom, you see that it turns to a simple point. That means now we can say with certainty that the atom is there. So the fundamental difference is that quantum entity has two forms of existence. When it is not observed, it is indeterminate and uncertain. When it is observed, it is definite and determinate. So when we do not observe, we see the atom. We do not know where it is. We simply know it is somewhere in this space. But where it is, we do not know until we do not observe it. But when we observe it, we say with certainty that the atom is here and shown by this point. Okay. While in case of classical entity, you see that whether observe or do not observe, the state remains same, determinate state. Here you see that fundamental difference between the states. When unobserved, it is uncertain and indeterminate. When observed, it is determinate and certain. Okay, do you agree with this idea of this quantum entity, classical entity?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay, thank you. Now this was more clearly interpreted by Copenhagen School of Thought, led by Niels Bohr and Werner Heisenberg. Okay. So in fact, the question was how to describe the unobserved state of a quantum object. Okay. Basically, mathematically, how do we describe the quantum entity? Copenhagen interpretation states that the quantum entity consists of its degree of freedom and statement. Basically, as far as the quantum entity is concerned, mathematically it is not a single state vector or simple degree of freedom. It is a combination of both. It's degree of freedom and state vector. And the foundation of the quantum entity is its degree of freedom, which takes a range of value. This degree of freedom is a range of value, it's not a single value. So basically it constitutes a space. And this quantum degree of freedom is completely described by the quantum state. Psi, you simply call it as a quantum state, and it is nothing but a complex valued function of degree of freedom. Psi is a complex function of degree of freedom and is an element of state space. All physical observable quantities are obtained by applying Hermitian operator. So we have a quantum entity that describes by a state, quantum state, which is function of its degree of freedom, and observable quantity are obtained by applying Hermitian operator on this state. And this quantity, as already mentioned, is inseparable pair. Okay. Individually, degree of freedom is not quantity. Individually, the state vector is not quantity. The inseparable pair, that is the pair of degree of freedom and state vector, is the quantum entity. And experimental observation collapses the quantum state, and repeated observation yields the expectation value. So it is something like that. Experimental, you see that this is quantum state, this is experimental observation. So we see that this observation has collapsed the state of entity to this point. Okay. Originally the state is this. This is psi state. Basically psi, which is set of its, which is function of a degree of freedom. For instance, position degree of freedom. So when not observed, as I mentioned, the degree of freedom is a space, not a single value. It means the object is simultaneously existing everywhere. The object is existing simultaneously everywhere at a given time. But as soon as measurement is made, it collapses to one of its objects. And when observation is performed, then again it regains its position and another observation is performed. So a large number of repeated observation gives the expectation value for that dynamic equation. Okay, let us be quite concrete to realize the Copenhagen quantum question. Consider a quantum particle moving in one dimension. Okay. Very simple problem, a quantum particle moving in one dimension. Then its degree of freedom is the real line. Here is the crux. The degree of freedom is not its position. Classically we say that motion along a one-dimensional being position x1, x2, x3, x4, and every time we say it is x. But quantum degree of freedom is the real line. Real line means all the possible values lying on the real line are constitutes its degree of freedom. That means the quantum particle in one dimension exists simultaneously everywhere in a real line. That is, the degree of freedom is this x, and where x belongs to any value from minus infinity plus infinity. So in that case, the state psi is now function of this r degree of freedom, position degree of freedom, and this position degree of freedom is a whole space or whole real line, not a single value. And a measurement projects the state to a point x, that is, collapse the quantum state to yield p, which is expectation value of operator O for state psi. That is simply the mode of psi state. Okay. And it is found that this p is always greater than 1, and when integrated from minus infinity to infinity, it comes out to 1. That means it obeys all the requirements to be interpreted as probability distribution. Okay. So the basic is, in order to describe a quantum particle in a straight line, its degree of freedom is the whole line. Okay? And the state is the function of that degree of freedom, which in turn is the whole line. And the position operator is applied on this state side. Then that particle is observed at a particular point x. Particle is observed as soon as observation is made. Particle will be observed at one point. But when the particle is not observed, it is everywhere on the line. This is the fundamental difference. And this is also from this diagram. Still it is indicating when it is observed, it is at a particular point. When it is not observed, it is everywhere in the space. But classically, no such phenomena. Okay. So, the complete description of quantum system requires specifying the probability for all the possible states of quantum system. Its possible quantum states are the different positions, and position of quantum particle is indeterminate as soon as it is not observed, and the probability is simply mode of psi scale. Okay. And this is the collapse of the wave function. So the moment the state is observed at a specific projection operator, the state instantaneously becomes zero everywhere. Again, keep this figure in mind. When this object is observed, it concentrates at this point and it becomes zero everywhere. That means the wave function associated with this particle will collapse at this point and it will become zero everywhere. Okay, and this collapse of the wave function is purely quantum mechanical phenomena. This is purely quantum mechanical phenomena because no classical waves undergo a collapse on being observed. The collapse of state is a purely quantum phenomena. For instance, in case of classical physics, we observe water wave. We never see when we observe the water wave, it gets collapsed. When we observe any other wave in classical mechanics, we never observe collapse of the wave. But here, as soon as we observe the wave function, it collapses everywhere except at the position where it is observed. So this is new to the concept. This is a foreign concept to the classical physics. So there is no such collapse of state in classical physics. And then the in quantum mechanics, wave mechanics, initially it was termed as wave mechanics. Since the Newtonian description of particle by trajectory was replaced by state that looked like a classical wave spread over all the space. So wave mechanics, because it was expressed in terms of the psi function, and which is called the wave function, because it looked like a classical wave which is spread over all space. Hence the term wave function was used. The state function of quantum particle is not a classical wave, as we have just seen. It collapses as soon as it is observed, but no classical wave is collapsed after observation. But still it is called a wave only because of the fact that it has in common with a classical wave that it is sometimes spread over space. Just like the classical wave is spread over space, this wave function is also spread over space. In that connection, it is called wave function. Otherwise, it has nothing to do the wave in classical physics. Okay. Then, now because of this ontological existence of the classical and quantum, classically we see that the particle exists objectively. Objectively means the particle exists in the same state irrespective of the fact that it is being observed or not. So it is certain objective and definite state. Therefore, we can track the trajectory of the classical particle regardless of the fact that whether it is observed or not. Okay, as shown here, let us say at some time Ti, the particle is at this position. At time Tf, the particle is this position. We can track this path, whole path. We can tell at this time particle as this, for instance, at time the particle is at position xt having velocity vt and so on. So classically the path of object is objectively existing because its position is because its ontological existence is also objectively existing. So the existence of classical object does not depend on the fact whether it is observed or not. Similarly, the trajectory of the classical particle exists objectively. It does not depend whether it is observed or not. But in quantum mechanics, as we know that the position or the existence is of two forms. When it is observed, it is definite and determinate. When it is not observed, it is indefinite and uncertain. Similarly, if we see the path taken by a particle, when it is observed and when not observed, we find there is a difference. For instance, when the particle at Ti, it is at position xi, it is observed. Okay. At Ti, particle is observed, it is found x. At Tf, the particle is observed at x. These are the experimental. But in between xi to xf, let us say there are n slits. So, we know that at time Ti, time f, rho, particle, usually go and so on. We are completely unaware. We do not know through which slit the particle has passed. Because we have not observed quantum mechanics, we do not observe, we do not know with certainty. But at Ti we have observed, we know with certainty. At Tm we have observed, we know with certainty. But if we show just like the ontologist of the concept, its path is also having two forms of existence. When it is observed, then we can say that this path is infinite, the particle is following this path. But when we do not observe, we do not know path. The path is indeterminate path. Okay. So when it is not observed as indeterminate, then it is indeterminate path, and this indeterminacy of path is realized by the quantum process. Once again, we can say that if we do not observe the intermediate path, so we can say that the particle remains certainly only path. This is very cognitive idea as the existence of the quantum objects simultaneously at various places at the same time is quite quantum counterintuitive idea. This idea of indeterminate quantum path is also counterintuitive idea. It can never be realized experimentally. It can only be verified through the observations. So experimental observations are the ultimate test of the quantum mechanical ideas. Uh, Let us, how do we describe them if we do not know through which path the particle is going? We can describe it just by assigning a probability amplitude to the determinate path, saying with certainty that particle is going through path x1, x2, x3, xn. We say that there is a probability amplitude associated with path x1, let us say phi, associated with path x2, phi2, associated with path xn is phi n. So we associate the probability amplitude because it is uncertain. With certainty we cannot say. Okay, let I be the probability amplitude for a particle that is observed at x1 at time t1 and then observed at xn at time tf. The probability amplitude for the transition is obtained by superposing the probability amplitude for all indistinguishable determinate paths. That is, this phi is simply summation of phi n, the total probability amplitude. And the probability is simply the mode scale of the probability. The probability is the mode scale of the probability amplitude. So, using this concept of the indeterminate path, one can explain the observation of two-slit experiment, popularly known as Young's double slit experiment. All of you know very well the Young's double slit experiment when light from the two narrow slits is observed on a screen, then one observes a interference pattern. Okay. So can we explain this interference pattern by applying the idea of the determinate or indeterminate path? So which is, let us we try to explain the observation of these two-slit experiments through the concept of empirical and trans-empirical paths. Empirical means the path when it is observed. Trans-empirical path that cannot be observed experimentally. Anything which is not observable experimentally is trans-empirical, and any phenomena or anything which is observable experimentally is empirical. So in classical mechanics, we know classical entity takes a determinate path going through either slit at position 1 or two slit at position x2. That is, let us say one is at slit x1, x2. So we know the path is determinate and can be result of two slit experiment can be explained by postulating that when quantum entity is not observed, path taken by the entity is indeterminate, and if this indeterminate path is trans-empirical. While that means the path quantum entity simultaneously exists in both paths. And superposition of quantum state vector, which is due to linearity of Schrodinger equation, is valid for indeterminate path. That is, for a particle taking indeterminate trans-empirical path, probability amplitude of going from an initial to final position is shown to result from quantum superposition. Let us see how it is this. Okay, let us see this experiment when two detectors are used. That means here it is shown that the quantum objects, these quantum objects, these may be photons in case of light, these may be electrons. So if these are photons, then you see the optical interference. If these are electrons, then you see the electronic. So let us first see this experiment when the detectors are placed at position at this position at slit 1 and second detector at position with slit 2. So electrons are coming out from its source, and when this electron is detected at slit 1, it means we know certainty that the electron or this photon is following this path. And once we know the determinate path of the object, then it behaves like a classical particle. If we know the path, a determinate path, then that behaves like a classical process. So when we do detector here, the electron passing through slit S1 is detected. It means we can say with certainty the electron or the particle is following this path, then it behaves like a classical particle at a distribution like this P1 is observed on the screen. There is a maximum intensity in front of this slit and that intensity is lower on both. Similarly, due to this detection 2 placed at slit 2, it confirms or it ascertains that the electron is passing through the slit 2. So once again, we know the determinate path, and if the path is determinate, it behaves classically. If it behaves classically, then its distribution on the screen will be this P2 curve. That is, it is the peak in front of this slit 2 and then smaller on both sides of this P. So this distribution curve for electron that passes through slit 1 and disappears. Now, electron 1 is passing, some electrons are passing through slit 1, some electrons are passing through slit 2. So the total distribution of electron on the screen is that shown by this 3 curve, that is PD, the distribution curve. That is simply the sum of P1 and P. The PD is P1, P2, P1 plus P2. So the net conclusion from this diagram is that when we place detector at both the slits, that means when we observe the path of both the electrons passing through the slits, then they behave classically. And they behave classically. Now, when there is no detector, let us say we remove the detector from both the slits. Now, how to describe the slits? As I mentioned earlier, if we do not observe the path, then the path is an indeterminate path, and we assign a probability amplitude for an indeterminate path. Let phi 1 be the probability amplitude for path 1, phi 2 be the probability amplitude for path 2, and phi be the total probability amplitude. That is, no detector is there, so this electron coming here is simultaneously going through this slit and this slit, and when it is observed, we say it is. So, phi 1 is the probability amplitude for this path through slit 1. Phi 2 is the probability amplitude for this path through slit 2. And phi is the total probability amplitude, which is phi 1 plus phi. And we see that on reaching the screen, measurement of electron at screen detector collapses the trans-empirical probability amplitude to its empirical manifestation, mod phi square. So the probability at the screen, this phi is the probability amplitude. Probability corresponding to this probability amplitude is its mod square. That is mod square of this phi. That is mod square of phi 1 plus phi 2. So mod square of phi 1 plus phi 2 will be mod of phi 1 square plus mod of phi 2 square plus phi 1 phi 2 star plus phi 1 star phi 2. So here you see that this mod of phi 1 square is simply this curve P1, probability of passing electron through slit 1. Phi 2 mod square is this curve P2, probability of passing electron through slit 2. And then there are these extra terms, phi 1, phi 2 plus phi 2, phi 1, phi 2. So these extra terms are the independence terms. The presence of these terms ensures that there occurs an interference, and as a result of that interference, this green curve is observed like this. And this green curve is nothing but simply the interference pattern obtained in the two-slit experiment or the young double-slit experiment. Okay. So this phi1, phi2 term is the interference. The important point to note here is that when the trajectory of electron is not experimentally observed, as in case of this, no detective there, trajectory is not observed, then single electron path is indeterminate. That is, electron received at the screen detector simultaneously comes through both paths. This electron is moving through this path, the same electron is moving through this path and observed at X. So, electron received at screen simultaneously comes through both paths. In other words, through both slits. So, we can say electron interferes itself. So, this is very fundamental point which Dirac highlighted in connection with the interference of photon. He used to emphasize this term that the photon interferes with itself. So clearly, one can never directly observe a single electron simultaneously going through both slits, or of having an indeterminate path that requires a single electron to simultaneously exist at two different paths. So we can explain this interference by employing the concept of the indeterminate quantum path and the concept of the indeterminate quantum of existence when the object is not object. So I think we stop here, or shall I continue? Anyone, please? Shall I stop or continue?
Good afternoon, sir.
Very good noon.
Sir, I think you have other lectures also, so you can continue later from this.
I have another one more lecture that is on tomorrow.
Yes, sir.
But that is actually a lecture on the nuclear reactions, not on quantum mechanics.
Okay.
Anyhow, you find it sufficient time is not.
Yes.
Because
then it depends on you, sir. Whether you want to continue or because we already have completed the session's time of 1 hour and 30 minutes.
I think so. Our time has already we have concluded. So anyhow, let us discuss now if you want to discuss something regarding these concepts.
Yes.
Now it is
any questions?
Let us have 5 to 10 minutes for discussion.
Yes, sir. Any questions from the participants?
The conceptual aspect या कोई ऐसा कारण भी है बट जो है difficult है तो ये explain है
Any questions from the participant?
So most of you are college teacher or some university department teachers?
So most of them are all college teachers.
College.
Yes.
then you have to teach this quantum mechanics at a very fundamental level.
Yes, sir. So I myself find it very attractive.
Yes, sir. It
And
will be very
because
good for us if you share this.
Yes, pardon, please.